short and kind of in between. As you would expect, kind of in between is always the hard one, right? Ish. But super long, it's like having this little current going like this, leading to an M like that. And the M here, why? Oh, that makes sense. Because this is circumferential and it's across, it's M crossing them because that is your test, right? Then the next one, which is super small, which is nothing more than a loop, which is a physical example, right? And this would be just the K this way, fine, but super small. It would look like that with loops and loops, and bigger loops, and then going to infinity in the middle there. And then when the dimensions are roughly 1 to 1, still you get this K, you get an M. I have a better picture of that type of situation. And that one was hard to find in another problem later. Because a lot of people, the thing you're gonna find with it, and it doesn't show it here, is, well, actually it does. Do you see this? That's not orthogonal with the surface. It's not, it doesn't have to be.
The K?
No, the B field from it.
Oh, yeah. Yeah, the curl.
Yeah. And remember, magnetization, just like polarization, can't be on the outside. You can have fields and stuff, like from B. And perhaps another type of field that'll come up soon. Thank you. You read! Wow! It's exciting. It's like you'll learn things.
Wow.
So, that being said, we did talk about, or did we? No, I'm not allowed to show you that. Okay, so I can show you this H. The only reason why I'm doing overheads like this, the crappy looking ones, is because it's time. Otherwise, I'd write everything on the board like when we had more time, and it would be nicer. I apologize for that. Blame the school, complain.
I
True,
hope
don't complain to me.
I hope
Complain to the people who made that decision, okay?
I hope to.
They need to hear it, because everyone's against it. So we found what J sub P is. Well, I read that. Okay, we found what J sub P is. That's bizarre. And K sub B. And so now what we want to say, we want to bring in some new terms. We did that kind of thing before with some other stuff. So before, whenever we talked about,
Sorry, I got attention. Do you need help?
It didn't break, did it?
No, I just took I couldn't fit my coil upright in my car, so I had to take it out of the slot.
Right.
It just shuts back in.
Well, good, you made it modular. That's excellent.
Kind of. Okay, I have to go park my car. I'll be right back.
Yeah, don't get in trouble. I look forward to seeing this.
Me
It
too.
doesn't work.
It's okay. I will put my magic hands upon it, pray the proper way to the Enem gods, and it will work. I am the Holy One. Okay. So.
Do you have to do any sacrifices or?
Students in my class.
Nice.
Oh no.
The tears of my students.
I
So-
volunteer as treasure.
So the J's that you knew and you were comfortable with were the kind that flowed, right? Like from over there to over there. and that's true. Now we have a new J in town, and it includes a bound term, which is weird, and a free one that you're familiar with,
Yeah.
right? You good with that? Sum them together for total J.
That makes sense.
All right. And there it is, right there. Now, since we have definitions for J of B and K of B, we can utilize that. In this case, J of B, most generalized term, the test that we know, and we have that. So what we do is we rewrite it. Now, interesting thing here, do you remember this?
Mm-hmm.
Excellent, because now we take that J, and we get this one by itself. Okay? equate them to each other, so this side will then be equal to this with that underneath.
Yeah.
And we replace that JV. And when we do that, we get a new term. And you might think, oh, great, another one. I know, it's always one more term. And this is a weird one in itself, but it's actually one I really like. Because this one has interesting units that involve current, which means it's like a human-made term. You apply a current to get some result from something. And so it's H is actually kind of cool. Now, it may not be easy to see exactly what it means at first, but when you take this term and you have it in this form, because now you've got this curl, right? So here's that curl, but then you replace a few things and you get these two terms being curled, right? These two vectors. And the difference between those two things is equal to the actual free J. This is kind of like that, what we did with a D thing in a way, but the interesting thing about this one is that you can say that this new thing in town called auxiliary field will be equal to what the B field is minus a magnetization that occurs.
Yeah.
You will find that this is a very interesting little phrase, because in the end, it's the reason why magnets die.
Yeah. Oh, okay.
And so, it's a weird thing. The curl of that H is also equal to that, because that is H. I just replaced it. You got that. All right. Hey, just shake your head if you get it. If you don't get it, just do the other one.
Is there like a time component to it?
What's that?
Is there a time component to it? To be able to?
Not yet.
Maybe?
Shall see. Always. Okay. But look, there's an integral term too. You can determine the free current. Yes.
This is a little bit of a side question, but it does have to do with
It's
magnets.
okay. A lot of time I could bring up side things, so go ahead.
So I have this little like it was a pretty cheap like rice cooker, right? And it doesn't have like a digital
Safe,
display.
isn't
What's
it?
that?
Is it safe?
Yeah, yes,
Okay.
yeah. It was a safe. It's from like a legitimate source.
Okay,
and
okay,
everything.
good.
Yeah. But so recently I found that I couldn't cook rice in it because if I try to put my rice in there and then there's this lever on the inside that you click down on for it to start, but it wouldn't like click down. And so I took it apart and I found out that there was a magnet in there and a spring in there, which makes sense. Like it sits on a spring, but I didn't realize that there was a magnet in there. And my discovery, I think, led to the fact that the reason why it doesn't work is either the magnet is not as magnetic anymore from repeated use because it gets hot, right? And then, or something happened to the spring constant, right? Again, because of repeated use. 'Cause it gets
Clever thinking. I like that.
How long
So,
have you had that?
and I had it for like 2 years, I would say.
I would say the manufacturers were not knowledgeable about magnets if they were exposing them to temperatures.
There is a 1-year warranty on it, and
Then
then
there's that.
and then so the special thing is you have to sign up on a specific thing to get a 2-year warranty, and this breaks down like
Just replace
after
the
the
magnet.
after the 1 year. I'm not sure if I even signed up for the 2-year warranty, so I'm gonna try and email them and be like, hey, can you pretty please give me a new one because I'm a student and this is super helpful.
What you could do is put in a stronger magnet.
Yeah, or I break it up. I not break it, but tear it apart even more and then put a different magnet.
Yeah, a lot of times manufacturers don't, I mean, you can imagine what a pain it is to be around me when I get like a new object that I buy and I'm like inferior, you know? I get very frustrated because I'm like, who the hell designed this? You know, and I'm getting worried the more crazy things I start seeing. It's like, oh my God, this car, you know, it's like, I can't believe they did this in it. I mean, it just makes no sense. You start to realize that there's concepts of intentional, planned obsolescence, that kind of thing. Then you get things of, they could have made it out of metal instead of plastic, but then they wouldn't make as much money, that kind of stuff. And then you get just plain stupidity, you know? They had a product, it kind of worked, so they went with it. But they didn't do a whole lot of field testing. And certainly the K value, the Hooke's constant,
Yeah.
and, you know, can get messed up over time. It's what failed on the Phenom old versions also, I think, is springs start to fail so the door doesn't stay up. Same thing with hydraulic that hold up the back of your truck, windows. All that sort of stuff is like, it dies.
Over time, yeah.
Yeah, and some of it's just, it is what it is. What they need to do, and what I would force them to do if I were king of the world, would be forcing them to make it so that the object can be easily replaced with new objects without having to strip everything down and break it.
Yeah.
And so you know that the spring has a problem. You know the magnet's gonna lose its magnetization.
Yeah.
So what do? You make it so it's easily replaced. A little cartridge, boom, there it is. And then you don't have to throw the whole thing away.
Yeah.
And we live longer and a better life, right? I wish they would do that. And I think, I wanna say somewhere in here, like Sweden or somewhere, has some, maybe it's Switzerland, they said manufacturers have to take it back when it dies and dispose of it properly.
Yeah.
Because then it puts it on their onus to make a better product. Because they don't want it back.
They're gonna do
So,
with the dead product.
But yeah, but then, and then, you know, you feel like at least, you know, they're dealing with it, but at the same time, if a company has a good product and it lasts a long time, that's super important. I would say E&M in general is kind of becoming a lost art, it seems like, because I keep seeing a lot of weird things that people make and I'm not sure what the hell they're thinking. Yes?
I think I would definitely like pay more for a better product. Than
People are
like,
willing
yeah.
to. People are willing to. It's just the model that people are taking, and I don't care if you get this in the thing, is, and you can look it up on Wikipedia, it's called enshittification. And if N-E-N, it's a real thing, and there's even like an ad by like the government of Norway about this concept. And it's about making products worse. And
Yeah,
trying
in
to
order
make
for
more money out of it
consumerism, yeah.
and offering less. And when antivirus software looks more like virus software, it's like you know, it starts becoming a problem. And this is what a lot of people are doing, and they don't realize. I just wrote a nice little letter to Avast the other day. My feelings about your subscription, and brought up the enshittification. It is a real term, and it's what's happening with a lot of products. So it's something that, you know, be aware of it, and really what we should do is you know, ban the products that do that kind of stuff. I try to figure out how to like repair things all the time, so I'm not at the mercy of a lot of, you know, companies. You know, I want to work with them, not against them. But if they have a philosophy where it's just make money and they don't care, then it's not going to work well. So anyways, H, very cool term. When we had D for Gauss's law, look familiar?
Yeah.
That was also about free things,
Yeah.
like free charges,
Free charge
right?
versus.
Yeah, there's a lot of similarity here, but these are free currents.
Yeah.
It's weird. So it's Ampere's law for free current.
Yeah.
But I find it interesting because H, a lot of engineering people use H instead of B. I can understand why. There is a relationship there, you know? And so the question is, how do you utilize this? So how could we look at it? There's that problem we did with charges and dielectrics and stuff. Was it free? Can I show you that? No, can't show you that yet. Because I haven't mentioned something. I want to go back just a wee bit and talk a little bit about magnetism. Paul exclusion principle.
Oh,
You familiar with it?
yeah, we just talked about this in thermo
So
today.
you're experts, excellent.
I wouldn't say that.
Yes,
Okay.
yes.
I know.
You know about it, okay. And it has something to do with the electrons, protons, those little things, you know?
Yeah.
Fermions, that's what we call them.
Yes, sir.
And there's things about, yes, the periodic chart and stability.
Oh.
Very interesting. There's other things involved in that too, but I would say that's pretty cool. Momentum operator, you ever heard of that one?
Yes.
R cross P thing?
Yeah.
Yes, and then you've got the no spin electric charge gradient operator. Familiar with that? You probably heard of that stuff. All fermions
Yep.
have half integer spin, right? You know what a photon is? Don't look. You know what a photon is?
So those
And what's the spins for that typically?
spin zero.
Integer spin?
Did you
Did I
say?
write it up there? Jeez,
I didn't look
Well,
at
we just did, we had thermo this morning, the three of
Yeah.
us. We had thermo this morning, promise.
This is
What else does?
Helium.
Like gluons and things like that, right?
Yes.
How about gravitons?
Graviton.
Not up here.
Yeah, it's not.
What is it?
Graviton is a
Hypothetical particle for.
What spin do we think it might have?
I think it's been 0.
Think
Yeah,
so?
yeah, because isn't it supposed to be really similar to photons because it travels. at
They
the
have
speed?
no mass, right?
Yeah, no mass.
Let us see. Is that your final answer?
That is my best guess, yeah.
I don't think it's right.
Okay. What happens if I'm right? 2% credit.
You get me a Boston cream donut.
Hey, you're not allowed to have those anymore.
How do you know that? Talk to my wife?
I'll
No.
tell your wife.
So you still think it's 0, huh?
Mhm.
Yes, sir.
It's 2. Just want to verify. Its effect is as it passes by, it shrinks space in one direction, shrinks in the other direction.
Yeah.
So that's how LIGO works.
Oh, it's 2-dimensional.
So what happens is you end up getting shrink and expand and stuff.
Interesting.
Ooh, look at that little UFO. This is Roswell technology here. It is. It'll be fun to watch that. So, exchange interaction, are you familiar with that one?
You want me to move this? I just didn't want to get bullied anymore, so I came back.
What?
You can sit here if you want.
Overlapping? Exchange? Okay. If you had 2 spins like this,
Yeah.
over time you'd get that. But in ferromagnetism, not quite.
Just want to be more
Wait,
close to
why
the community.
do you like that?
Why is the big question. Why?
Is that for fermions or boson? Would it be because that's the least energetic state, and so it, over time?
The energy
disorder?
is the entire reason behind magnetism here.
Okay.
Not just one term, but a zillion terms.
So, it would.
Antisymmetric wave functions,
Yeah, yeah, we just talked about that.
all scrunched into one little thing, probably a whole lecture, you know. There it is.
Very-
Yep.
Just do like a review for later.
So, if you have, the thing about magnetism in these domains, you've heard the word domains,
Mhm.
is that a bunch of these domains can add together in these weird materials and be up to a certain size, and then suddenly a wall occurs and you get a flip to something else, and this domain wall. And so you can get like up to 1,000 of these little ions making this little domain. The thing that magnetic memory and all this sort of stuff was trying to do, and still trying to do, is to make those domains smaller, but you can't get beyond a certain size. And if you do, they become unstable. So you can start having bit flipping. The Voyager data and stuff like that on those magnetic tapes,
Yeah.
they're just not stable over time, so they've been losing data so fast. The ones that started getting lost, there's like more and more and more. So what do you do with it? Put it on another medium, let's say a CD. Let's say the CD starts to lose its memory somehow.
Yeah.
Then you have to go to the next one.
Well-
The only thing that's really good is you take a pyramid made of stone, and you carve all those ones and zeros into it, and it lasts like a really long time. Yes.
Well,
They have glass now.
Of course.
They have.
You can do that too.
And is this disorder
That's-
because of entropy?
That is one term. Let's look at all the terms. Are you ready for all the terms?
Yeah.
It's painful.
Oh boy.
Bring it on.
These are all the terms. You have exchange energy, magnetocrystalline anisotropy energy, magnetoelastic energy, magnetostatic energy, domain energy in the presence of an external field. All these are added together. The wall energy is right there. That's a lot of energies, man.
Holy.
All those energies go together, and still, we don't completely understand magnetism. But this kind of works. So basically,
It's good enough.
these things align, but not beyond a certain point. The energy's not right, and it can start to flip. And so once that occurs, you can start seeing changes. One of the things I did a long time ago was try to figure out how to image these kinds of things. And believe it or not, it's really interesting. You can take an electromagnetic field from a laser, hit a surface of magnetic field, things and domains, and it comes down, bounces up, switches a little, comes back up. So it turns out it can rotate and change depending on the magnetic fields down there.
Do you have a
Gains
metal?
the energy from it.
It's a material with domains.
Is it because of scattering or like?
Stuff.
So like how do you-
So it's called Kerr optical imaging.
Kerr?
There's transverse and whatnot. Yeah, they're Kerr, K-E-R-R.
Like black hole. Kerr.
Maybe a relationship. Sometimes these names come up a lot for different sciences because they do a lot of things.
Yeah.
But this Kerr, longitudinal, transverse, these modes allow you, depending on the orientation of the fields, can change the electromagnetic field coming in. It's small, but it's still like a measurable under 5 degree change of some kind. And there's a local company that actually makes a device that measures that kind of stuff.
Interesting. Why would you want to measure it?
Okay.
You gotta stay on topic though. We can talk
Going
later.
back to chapter 4. Is that allowed?
Yeah.
Okay. My field comes in,
Hi.
polarized a certain way.
Hi.
I hit a surface of some unknown material. It bounces off. They see a change. I take that same light and I rotate it slightly. I do another measurement, do another measurement, do another measurement, do another measurement. I have a polarizer in front of a detector, by the way, is here. And this light is polarized coming in. But as I'm rotating it on that surface, I'm getting information on the other side. Do you know what that tells me?
So you have light that's polarized, comes in, rotates, goes back up,
Changes.
changes, goes back
Goes
up.
back up. This is
And-
beyond, this is not necessary, this is going, you're asking about the technology, why would you want to know that?
Yes.
Or do you want it, and I'm answering that one right now. Then the question will be, the magneto-optical interaction. Why would you want to do that? What the company sells a technology that has something called a photoelastic modulator, and the idea behind that is it starts to rotate the polarization and rotates. You know how you have like a linear polarizer, and you
Yes.
can just take it and rotate it by hand.
Yes.
But this thing rotates it super fast. The
Interesting.
problem is it can't stay still. It has to keep rotating. If it stays still, the effect goes away. It's the the only way it works is by going fast, like 100 kilohertz or something like that, or 50 kilohertz. So if you don't have it going fast, so you have to have something that automatically senses its position, gets the data really fast, and goes to the next one, goes to the next one, goes to the next one, and keeps doing the data super fast. And you have to get it out of a lot of noise and stuff. So it's a very interesting technology. It's very unique. But that idea then of rotating polarization in general and having it rotate while you're taking this data, getting super fast data instead of going, what is it now? What is it now? What is it now? Turns out that's called an ellipsometer.
Eclipsometer?
Ellipsometer.
Ellipse.
What is an ellipsometer?
I've heard of that before.
And you should know what it is if you're in Raj's lab.
Is it to measure index? Index of refraction?
Permittivity.
Permittivity.
And index.
He's holding out on us.
He's got one, I think.
He never tells us it's his
Maybe
toy.
it's broken. He's got a lot of broken stuff. I know, he needs to fix some of that stuff.
So,
Epsilon K.
that little rotation that happens can tell you a lot about the material's properties.
Everything about the materials. It's hard to kind of backtrack it, but yeah, I've got like a manual one in the lab, and someone was going to make it automated for me in 316 years ago and never did. Then another person tried, then another person never went anywhere. It's still there, you know, but I could put my PEEM on it and make it automated myself. I already wrote the code for it, but it'd be nice for like, you know, a student to play with that and learn about that. They're automated systems, and they're ones that are even change the color of the light and then does a rotation. And then that gives you like really good information about the material across the whole spectrum and the permittivities. But it also, reverse engineering stuff can also start to tell you like thickness of materials, stuff like that. Now, the magnetic field stuff, now we're chapter 6, right? The reason why that stuff was important a while back is because if you could fix the domains in a certain orientation with like a little magnetic solenoid and put it down at a surface and then force the magnetic field a certain way, you could force the domain into a 1 or a 0, 1, 0, get it? So they had something called a magneto-optical drive. Very pretty discs, it looks very prismatic, but it was like a first version of like a CD. And it used that concept for reading back.
Wait, what?
A magneto-optical, your head's gonna explode. I can't take it, there's too much information all at once. Okay, the magneto-optical drive went out of favor for probably speed or density, I don't know what it was, but like many of the things like Laserdisc, right? It's gone. You could store a lot of info on it, but people wanted more and more and more. And even with the magnetic storage, if you remember the very first form of magnetic storage, they would find old ladies who would take a needle and a thread and thread these little beads and put current through these wires, those threads that they were putting. They would literally hire them to just sit there and just do this all day. And they made these magnetic memories, and they were ferrite beads, and wires would go through them, and when you put current certain ways, you could store like a 0 or 1 or whatever, and then read it back. But they were like 100 by 100. That's not a lot of memory, you know? And just think of those poor ladies just all day long just sewing that stuff up. It was a lot of work, you know? They didn't have the automation back then, and so I think eventually they probably did, but that's what they had for the magnetic memory. It was a big advancement over, you know, relays. Because now you can store 1s and 0s in different ways and whatnot in a smaller region. And then eventually those disappeared, and magnetic memory kind of disappeared as a whole when you started getting like CD-ROM, stuff like that, you know. And so after that, we still have magnetic drives being sold. So those still have pretty good density, but eventually those die too. They're mechanical, so you'd expect they're gonna die. And still there's a bit flipping thing, right? I mean, there's something to be said about this solid state stuff, but you have to remember that you can only have so many reads and writes and then the thing dies. And a lot of times what they'll do is they'll put reads and writes in different regions and saving things in different regions to use up as much of it as you can, have an algorithm for all this stuff. So that way they don't just keep trying to put stuff in one region, because then they'll die faster. So it's all very cleverly done. We don't have anything that's perfect, but as I always say, back it up, because you're gonna lose it. It just happens. Now, the other thing about the domains is sometimes you make a new material and you wanna know what the material is. So if you have a Kerr imaging system, that would tell you a lot. Dichroism, another thing. You don't always have, if you wanna know the orientations of things, dichroism is a way of looking at that. There's a thing called also the Stokes parameters, matrix elements. Yeah.
Stokes theorem, sorry.
It's a matrix that tells you about the material magnetically and whatnot. It's stuff we're not going to get into, but it can do a lot of things. It is a bit nichey, I'll be honest, but the company is local, and I'm going to meet with them relatively soon. I have one of their units, and I'd like to use it for the class. And so I want people to try out an experiment like that. So we'll see what happens. But I would say these domains and these small things are pretty cool. Imaging them is a little bit tricky. You could technically, and this is one of the things I tried to do a long time ago, but I think with my programming being a lot faster now, I think I could probably come up with a good answer for it. You have these domains and you want to view them, and the processing would occur because you have polarized light that's changing very quickly through a beam, and you're picking it up on a camera that is looking at differences at a very high rate. But the only way you could do that is by having asynchronous readout. That's the key. Normally when you have a camera, there's only a couple with asynchronous readout. Normally it's like, it always puts it out at a certain time, and that time's always the same.
Does it store it somewhere? So you can...
Yeah, I mean, it will in some kind of what we call DMA transfer buffer or something like that. It saves it to some memory, but the problem is it's always like the same rate of read out. And so you need one that you can read out according to a lock-in synchronization signal, which allows you to like now, kind of now, a little later, maybe a little earlier than now, and keeps doing this. And if you do that, then the camera is asynchronous. It's being called to pull an image when you want it or when you need it, not just regularly in your, that's
FPS.
mercy of its
Yeah.
synchronization. So as this PEEM is changing its characteristics, you need to be able to have it take the data when it's ready,
Then it's changes.
when it's at the right point.
Yeah.
And so timing that is very critical. And if you do that, then you get different polarization images. Then what you can do is look at those different polarization images and make some kind of difference image or something like that. I gotta look into it. That's why I need to talk to them about, do you guys have a simple demo that you've come up with in the past to show people? Because I don't want to reinvent the wheel if somebody's already done it. But the good news is I have a lot of cameras and I think you can asynchronously pull the data out with a trigger. And I think it's fast enough to be able to get the data for that. And if you can, then it'd be cool imaging. We'll see what happens. But it is about how many atoms are in the domain roughly. And this is very rough, okay? Very rough. It's not just one atom. If you had a one atom magnetic domain, you violate a whole lot of things. But man, your memory storage would be incredible. Reading would take 1,000,000 years, but you would have like the best storage in the universe, right? One atom, 1, 0, 1, 1, 1, 0. It would never survive. It would flip to make a domain because of all this stuff.
Interesting. So like right now, instead of flipping, we have like a whole group of electrons.
Yeah, and they're going to be in 3 dimensions. You're going to have a material that has in 3 dimensions these little domains, these little dipoles that are all aligned to each other, but they can't keep going farther and farther out. Eventually, you get a flip over here and a flip over. That defines the wall.
How strong is the Earth's magnetic field?
Weak.
So
10
it,
minus
like,
4. I mean, it's like,
well, I mean, like, how much of an effect does it have on these domains?
oh, if you heat them up to the Curie temperature, 100%.
Ah.
But you have to heat them up, then it'll cool down. But is it perfectly all aligned flawlessly? No, nothing ever is 100%. There's always a little bit of randomization, but in general, orientations would be in one orientation.
Stuff.
Yeah.
That's what, okay. So
But
that's what,
this is more like tailored materials and compounds that you like want to make smaller domains. But okay, you may achieve it for X amount of time and it won't be useful after a certain point.
So how would do we need to apply electric field to be able to change the?
No, you usually apply it on a magnetic field, but that's what the read-write head is, right? So if you look at something here, let me see if I can find it. Read-write
That's so cool.
head of a hard disk.
That's why it should have been a EC,
What's that?
major or computer architecture.
It's not too late.
Not too late.
It's not too late.
What are you saying?
Saying that it would be cool to like learn more about like computer architecture and stuff.
That's one of the things I try to teach people in 316, but did they listen to me? Let's meet and do some computer putting together. Who shows up? I did.
I would have.
I offered to train people on computers. You had already left, I think.
oh, okay. I would have been there.
Who was there?
I would have been there if I was here.
I don't remember that.
Uh-huh. Same answer I get from everybody. What?
I wasn't there.
What did you- huh?
I wasn't like that.
So, this is what a head might look like.
It's before
This isn't the
my time.
best of these, but
Okay, take it 360.
I think you do it better than that. It's not that small, right? There's one. So, yeah. Another thing is these things go over the surface incredibly fast. Now the weird thing is, from what I gather, they put a small mist of oil on there, or some liquid or oil, whatever, on top of the platter, and it's supposed to fly over and have an interesting effect over this thing, super fast. But as the drives get older, they get sticky. It's called stiction. And then suddenly you turn on a drive and you hear a ticka 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 as it's like trying to unstick itself. You can smack it with a hammer, don't smack it too hard, and it will let go of the surface, and then it'll be okay. That's a good warning. Get another drive fast, because you're going to lose it. You have to know how to hear it first. You can hear it if you're good. But these are like drive heads and stuff.
Are you the hard drive whisperer?
No, unfortunately, and I have several drives to prove that. There's your drive head, your reading and writing.
Wow. That's so cool.
And they're strong neodymium ion boron magnets.
And these are all inside computers?
Oh yeah, and in fact, wow, yeah, see, I just assume everyone knows all this. This is common knowledge for my generation. So, and this is only 3 platter heads. You can have many more. You can have a drive head on this side, other side, this side, that
Hard
side,
disk
this
head.
side,
Oh,
this side.
this is what the
Your
hard
data
disk
is here.
looks like.
All your domains are here.
Uh-huh.
And this sucker's spinning at like 10,000 RPM.
How does it, so it calculates the RPM and then.
And knows exactly where it is at a certain time.
So those like motors there must be really precise.
Yeah.
So
Rip
you-
open a hard drive. I got plenty of them. You could, strong magnets, fun to play with. Yeah, no, these things are incredibly precise. What I find interesting, some, I don't know if they're all, but some are glass. And I had a hard drive that wasn't working, and I couldn't figure out what was going on. So I opened it up and I go, why are there clear glass discs in this drive? Because the head hit and scraped all the metal off. And I looked in the little filter fan on the inside and it was covered with dust. That was all my data.
Oh, no.
So yeah, they were all clear. It was glass platters. Pretty straight material, you know. Makes sense why you might have it. You can imagine a catastrophe if you smack. Well, that's why you don't hit them, right?
So you shouldn't really hit any.
But they're always spinning, doing an amazing job. It's amazing they work at all for as long as they do. I got thousands of hard drives, but I've been trying to go to solid state. But what you want to do is just a little side thing, go to RAID. RAID allows you to have like, there's 2 different numbers. RAID 2, 3, 4, 5, these things. Normally when you have data, you just put it on the drive. You lose that, it's gone. But if you have RAID, it like doubles up in a weird compression algorithm such that when you lose one of your drives, the other drive, you can still recover all the data from it.
Oh.
It's an algorithm. So it's a very cool thing. And so you have the more you have, the more safe it is. RAID 5, RAID 7. I've never seen 7, but I do 3 or 5. So you have multiple drives, and you just don't lose your data. You just plug in hot, plug in, swappable another drive, and it automatically takes that data, puts it on the new one, even if the drive is lost. It's very clever, used for servers and stuff, but you can do it at home. RAID 0 is what most people use, which is where it's just, you put the data on your hard drive and that's it. You lose it, it's gone.
You should just put it in iCloud.
But in your BIOS, you can oftentimes set it to a RAID mode, just know what you're doing. Be aware, if you had 2 hard drives, now you have 1, right? You give up 1.
Yeah.
But that's not bad.
And so the little tip there, that's what.
Yeah, so the little tip, let me show you, hard drive head. Yeah, the read and write sections. There's your drives, the tracks, and sectors. You've heard these names before, right? You can like you can put you can put samples on it, like on a CD-ROM, time it so you go around and you can actually image a sample using the laser from your CD-ROM. Is that a cool idea? Just gotta hack it. There's someone who did it, but they charge a lot of money for it.
You can make like an AFM from it, or no?
Yeah.
Yeah.
But mainly optical imaging from it. Because remember, you have a laser in there. It has a focusing ability. It can go around and it takes in data and goes to a reading unit. So normally it's either a 1 or 0, but it's a very slight level. But what you do is you make it so that particular laser, which is 473 or something like that nanometers or something like that, 455, it's very strong, can go and do fluorescence imaging on this platter. So you put your fluorescence sample on the CD and just have it go around, but you have to time it so that you know that sector represents your sample. So what it does, it goes around, it goes take data, take data, take data, take data, you keep doing it in the next sector, and you keep doing that, and then you build an image based on it. And then the sample, you have to take the signal back from it and figure out how to like put a little filter in there to remove the excitation light and just get the fluorescence to come in. It's pretty cool.
Wow.
And
Interesting.
there's a lot to learn about that kind of stuff. Here's your. There's a lot that people have done over time. A little inductive gap read. You're reading here. There's a magnet read. Inductive right head, so you inductively create a domain in a certain way, and then you've got a read head for determining like a little GMR, giant magnetoresistive. What's that? I can't hear you.
It's cool, very cool.
It is, it really is. It's amazing stuff. What's so funny?
So if I were to buy like hard drives, I could maybe do like different projects with them, right?
Oh yeah, in fact, I wanted to do it for the longest time, but it takes time. It's a new shiny, and you have to be careful because you can spend a lot of time. There's a company that like sells you an educational CD-ROM that has like a bunch of pins in the back, which is like a normal CD-ROM that's just been tapped into, but they charge like a ton of money for it. Well, it's easy to get all the data for all the pins and what they all mean for data and stuff like that and control of the motor. So my thing would be, once you figure it out once and put a little bit of energy into it, make your own, and then set it up with the right timing, pull out the little filter, put in a new one, make it so it's good for the imaging, and have like a super fast, really small, multi-photon even possibly, scan system. You just put a new sample out of DVD and then you get your image. Right?
DVD sample.
Yeah, the DVD is your sample, right? Nothing wrong with that.
Good old physics.
And it's designed to do amazing focusing and, you know. So, a thought.
Good old physics lab.
I think it's pretty cool.
Let's go.
Yeah, that kind of stuff to me, I love gadgets like that because I find that that's the kind of stuff that you could learn a lot from. And I think it's good for people to play with stuff that's cheap, right? Because if you try to buy a multi-photon like imaging system, it'll cost huge amounts of money. You can't afford it. It's that simple. So now that you know that, I wanted to show, am I allowed to show you?
You are.
You can show us and
You're in
It's not-
charge, Dr. Sanchez.
It's not that, it's the amount of like where I can show you where we're at. It's not like,
We're at the end.
this is illegal, I can't show you.
We're at the end. This is the
Um,
end.
So,
We're gonna
really
do,
simple.
batteries.
As we had the Kaiser, this is a really short thing. Similar to your permittivities, you had a relative, not relative, ugly terms on units, vacuum permittivity. Same with the mu sub not, mu sub r, mu. And this is the stuff that's going to save your butt in CME. So, chi sub m, a new term. It's a multiplier. When you have H hanging out, it's related to the magnetization.
Oh, wow.
By what? A constant,
Whoa.
chi sub m.
So,
Dimensionless chi sub m. And it turns out we have these terms that we talked about before, right?
yeah.
So what we can do is say we've got something new in town. And the mu naught 1 plus chi sub m, just like before for the E stuff, becomes our mu. And so mu, as you would think, has also a relative value to mu sub naught to give you mu sub r. And mu sub r is the number that everybody likes to use because it's unitless. Right?
Yes.
That's so funny.
she corrected me.
Okay, it's all on video, by the way, so being recorded. Maybe you should worry. So I'll have to watch it later and see what you guys are saying. So mu sub r.
I'll make sure to
Here's
put it on
the-
YouTube so you can.
Here's the interesting thing, mu sub r, iron. Iron in the universe
Yes.
is, if you don't oftentimes find iron today in its pure form.
Oh, wow.
They've dug a lot of it out of the ground in its really pure form, in large quantities where it's really, dense and stuff. So they have to get iron from a lot of different things, in particular recycling.
Yeah.
Like a battleship, stuff like that. So when you get a big freighter or something like that, or a big cyclotron magnet, and they don't want it anymore, they recycle it. They asked me if I would recycle the one at Harvard, but that's large, made from a battleship from what I heard.
Oh, wow.
And it takes a very large saw to cut something 2 or 3 stories tall.
Yeah.
And so I said, no, thank you. Because that's not my business. But turns out these materials, iron is really amazing, has a really nice high value, but not as much as this guy that's gonna save your life someday. Got Havana syndrome? No problem.
What
If
is
you know
that?
someone's gonna attack you with it, that's what you use, Supermalite. But you have to know ahead of time, that's the problem. That'll stop it, at least decrease its effects dramatically.
For
What is
a bee
it?
field?
Yeah.
So I should just cover my head with Supermalite?
Okay, you're gonna look a little weird, but yeah. I'm just saying,
I just
yes,
feel like-
this would work. If you're afraid of aliens putting beams in your head, you get some mesh with that, you put it in your hat, and then you're safe, at least for that part of your head. If they attack you from below, maybe you're in trouble. But otherwise, yeah, put yourself in a suit of that stuff, make a room with that stuff, you're safe from CMEs, all sorts of goodies.
How do I make Supermalite?
Make is a little different.
How do I?
Let's talk about Supermalite.
Okay.
Also known as a form of new
How do you, oh,
Supermalite.
metal.
I wanna make my house out of
Super-
it.
that's a weird word.
New metal. I wasn't joking.
Perm alloy?
Supermagnetic.
Permalloy.
Or permalloy, or supermalloy.
Such a weird word.
Well, I know. It's just like inconel and, what is it? And super inconel. What is inconel?
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 INCONEL. Do your little typing there. Get it?
Inconel?
Oh, it's not voice controlled
Nickel,
yet?
iron, and
That's a bunch of things.
Yeah.
So it's all magnetic and stuff, right? But the interesting thing is that it's amazing at certain aspects. So let's talk about inconel for a moment. I don't have inconel up here, but
Oh,
inconel
okay.
is something that has a very, very low expansion, which is nice. One of the lowest expansions of metals. Very, very magnetic stuff too. Then you get another one called super inconel. God, what is it? Super inconel? Why am I not getting that right? Anyways, that material is bizarre because that one has a negative coefficient of expansion. In other words, when you heat it up with a certain
It gets
temperature range, it
smaller.
gets smaller. And you can make it, the problem is when they make it, they have to make it in one batch, and that batch is like pretty much all the same. So you have to use it for whatever application for that kind of thermal expansion coefficient. Whereas you make another one, it could be a little different. It's hard to make perfectly. Because if you have two materials that span differently, they could give an overall difference of what you don't want. So you want to make sure if you're going to use it for a cavity or something like that, that doesn't change shape at all when it heats up or cools down, you want to make sure you make it in the same material. So it's an interesting technical problem. But if you want something with super low, you get Super Seal? I think it's Super Seal or something. I can't believe I'm forgetting these names. It's like a glass that's incredibly, like 10 to minus 6 expansion more than normal. So it's like really, but it's hard to machine it. Whereas, inconel and I am not saying the right word. I don't know why I'm not saying the right word, but those materials are like gummy to machine. They shine up real nice, but they're very gummy. So it's like copper, so you might throw your piece and break your blade, break your bit. This stuff, soft magnetic alloy, that should tell you something. But you can see that when you get, see that should tell you about. Mill. What does mill mean?
Magnetic something.
Oh, is that what mill means? Mill?
It looks like a pattern.
Military.
Oh, I wasn't gonna guess
Ah,
that.
now we
Military.
understand. So if there's a nuclear bomb and it explodes, how do you protect yourself against the nuclear explosion? Because if you have just normal chips in your electronics, they'll just die. You'll induce currents in them, and the currents then burn out the chip. So as soon as the magnetic field goes by, gone. So you need wires so that doesn't happen. Old school. So turns out, yeah, so they have the whole thing that the government loves to have things that protect against EMPs, EMP like the coronal mass ejection back in 1859 that occurred.
Yeah, that's right.
Familiar with that one? You weren't there. It was terrible. Basically, sun puts out a lot of particles of a certain type that's bad, hits the earth real fast because this one thing went to prominence and then bam, faster it goes bam, the worse it is for us, especially when we're facing it. So what happens